Hello students, it's Nazia Begum here, your physics lecturer, welcoming you all in today's class. Today we are going to start our chapter 13, that is thermodynamics. Okay, in earlier chapter, previous one, we have already discussed about heat, temperature, and what is the effect of heat on solids and liquid, how they get expand. We have also discussed about mode of transfer of heat and about the black body. Now in this chapter we are going to study some more phenomena which is related to heat, temperature, okay, and that's why it is called thermodynamics. In thermodynamics we will study temperature in more expanded way. So first let's see the introduction. From our daily life experiences we have elementary ideas of heat and temperature which we have discussed in previous chapters, so I am not going to discuss it again. Now here we can see it is written caloric theory of heat. Okay, so we have assumed heat as energy. Okay, heat is a kind of energy. According to caloric theory, heat is regarded as invisible massless fluid. Okay, like air and water, they are fluid. Heat is also considered as fluid which is invisible and massless. That means heat is a substance here. Okay, so heat is here treated as a substance that fills the pores between the atoms and molecules of a body. Okay, and such a fluid is called caloric. So heat here is assumed as a substance which is called caloric. If caloric is added to a body, its temperature rises, and if caloric is lost by a body, its temperature falls. Okay, if a hot body is kept in contact with a cold body, caloric flows from the hot body to the cold body. See, everything whatever we have discussed about heat in previous chapter, everything is true here. Only one thing is different. Okay, everything is same, but one thing is different, that there we have assumed heat as energy, as a form of energy, and here we have assumed heat as a substance. Okay, all the other things are similar here. How the heat will flow from one object to other object with the effect of temperature and all, everything is same. Now let's have an introduction about thermodynamics. It is the branch of physics which deals with the concept of heat and work. It enables us to successfully analyze and explain the energy transformations involving heat, mechanical work, and other forms of energy. Okay, so here we will basically discuss about different works which is done by heat. These transformations in turn manifest themselves in the bulk properties of matter. Then here you can see it is written, a thermodynamic system represents an assembly of very large number of particles described by thermodynamic variables and parameters. Okay, so whatever thing about which we are going to study, that is called a system, and a system is made up of so many particles, and to study that system we have so many parameters, thermodynamic variables or parameters, for example pressure, temperature, volume, etc. And everything outside a thermodynamic system that directly affects the state of the system is called its surroundings. So whatever part we are going to study is called system, and except system, all the other thing which is surrounding the system is called surroundings. Now first let's discuss thermal equilibrium. So I will explain you it in very short. Two systems are said to be in thermal equilibrium if they attain the same temperature while in contact. So here we have two systems A and B. Okay, these two systems are kept in contact. The variables, the parameters, okay, thermodynamics parameters, pressure, volume and temperature, for A is PA, VA, TA, and for B it is PB, VB, TB. Okay, when they are kept close to each other, in contact with each other, with a conducting wall between them. Okay, so that time if they both are having same temperature, okay, so this parameter becomes this one, PA dash VAT, PB dash VBT. So here you can see that now TA and TB is not there, only T is written. That means the temperature is same for both the system. So this type of system where temperature is same, that is called thermal equilibrium. Okay, then let us discuss thermodynamic equilibrium. Don't be confused here, it is only the thermal equilibrium. When the temperature is same, that is called thermal equilibrium. Now let's discuss thermodynamic equilibrium. Okay, it is a more general term to be distinguished from thermal equilibrium. It requires that not only the temperature but other thermodynamic variables describing the system do not change in time. Okay, like pressure, volume, etc., they should also not change with time. So thermal equilibrium is only related with temperature, but when we talk about thermodynamic equilibrium, so here all these three equilibrium, thermal equilibrium, mechanical equilibrium and chemical equilibrium, all of these should exist simultaneously. Okay, thermal equilibrium means the system and its surroundings are at the same temperature. Mechanical equilibrium means there is no unbalanced force inside the system or between the system and its surroundings. Then chemical equilibrium means there is no change in the composition of system due to a chemical reaction, etc. Okay, so when a system is in thermal, mechanical and chemical equilibrium at the same time, that system is called as thermodynamic equilibrium. A system is said to be in a state of thermodynamic equilibrium if the thermodynamic variables describing its state do not change with time. Now let's discuss zeroth law of thermodynamics and temperature. Yes, you heard it correct, it is zeroth law. Okay, we are having first law, second law, third law. That is not enough, that we are also having zeroth law. Now I am waiting for any discovery that some scientist will say now it is -1 law, -2 law, like that. Okay, jokes apart. Let's discuss zeroth law now. So here in figure you can see three systems are there, A, B and C. Okay, system A and B, they are isolated with each other. Okay, that means A and B are not in contact with each other. So this is one wall which is separating both the system. This wall is non-conducting. So between A and B, no heat transfer is there. Okay, no heat transfer is there between A and B. But A and B separately are in contact with C with conducting wall. Okay, here A is in contact with C with a conducting wall here. B is also in contact with C with a conducting wall here. Is it clear? A and B are two isolated systems, they are not in contact. A is connected with C and B is connected with C. Now, if A and B are in thermal equilibrium, thermodynamic equilibrium, and B and C are also in thermodynamic equilibrium, that means A and B are also in thermodynamic equilibrium. A very simple rule to understand it: if A equals to C, B equals to C, so obviously A will be equals to B. Okay, so according to the zeroth law of thermodynamic, if two systems A and B are separately in thermal equilibrium with a third system C, then A and B are also in thermal equilibrium with each other. So what is temperature? Again from zeroth law, we can define temperature as The thermodynamic variable which has equal value for two systems in thermal equilibrium is called temperature. Okay, this is the definition of temperature by zeroth law. Next topic is internal energy of a system. We know that a given system consists of large number of molecules which have kinetic energy due to their random motion and potential energy due to the mutual force of attraction on one another. Okay, two types of energy they are having. Depending upon the physical state of the matter in the system, that is solid, liquid or gas, the kinetic and potential energies of the molecules may be very much different. For example, if the system is a solid, the potential energy is much greater than the kinetic energy, because in solids the molecules cannot move. So obviously kinetic energy will not be there, and if it is there, it will be very, very small. Okay, but in gaseous form, the molecules are away from each other, they are in continuous random motion, so that's why kinetic energy is very large in comparison with the potential energy. As mentioned earlier, the kinetic energy of the system as a whole is not relevant in thermodynamics. Therefore, internal energy only comprises the disordered energy associated with the random motion of the molecules of the system. It is important to remember that the random motion of molecule is not only translational, where the molecules move from one point to another in the container, but also the rotational and vibrational motion of the molecule. Is it clear? If we are having a container, so molecules are not only moving from one wall to another wall, but they rotate in their own, about their own axis, they vibrate. So different types of kinetic energy exist there. Internal energy is defined as the sum of molecular kinetic and potential energies of the system in the frame of reference relative to which the center of mass of the system is at rest. Okay, and it is also considered that the internal energy of an ideal gas is purely kinetic, because gas is having more kinetic energy in comparison with potential. So if a gas is pure, ideal gas is there. Okay, so in ideal gas there should be no potential energy and whole energy should be kinetic only. And internal energy of a system is denoted by capital U. Okay, internal energy of a given mass of a real gas depends upon its state described by specific values of its pressure, volume and temperature, and not on how the state is obtained. Okay, it does not depend on path, it depends on the variables only, the final position of the variable. Thus internal energy is also regarded a thermodynamic state variable of a gas along with pressure, volume and temperature. Now let's discuss some methods of changing internal energy of a system. So the first method is by placing the cylinder in contact with a body at a higher temperature than that of the gas. Okay, in this case what happened? The gas will slowly absorb the temperature from that object. Okay, from that body which is at high temperature, slowly the gas will absorb the energy and hence its internal energy will increase. Okay, due to temperature difference, the energy will flow from the body to the gas, thus the internal energy of the gas will increase. Second is by pushing the piston down. So here you can see one container is there. Okay, in this container this is one piston, it is movable piston. Okay, this one is piston actually and it is the handle. So if we push the piston in downward direction, okay, that time what happened? The volume of the container will decrease. Initially the gases are moving in the whole container, they are having large volume. Okay, but if we push the piston in downward direction, the volume of the container will decrease. When the volume will decrease, the pressure will increase. Okay, so the collision between particle also will increase. because initially the particles were having more place to move, but now they are not having enough place. Okay, enough means they are not having the same place, but now the area in which, the volume in which the gases can move has decreased. So when they move, they will collide each other uh, with more intensity, okay, and with the wall of container also, and because of collision, kinetic energy will increase, hence because of collision, heat energy will increase, hence the temperature will also increase. So these are two methods to increase the energy of a system. The internal energy of the system will decrease if either the cylinder were placed in contact with a body at a lower temperature, or the gas was allowed to expand by moving the piston up. So whatever thing we have done to increase the energy, if we do the opposite thing, so obviously the energy will decrease. It is thus clear that heat and work are two different modes of changing the state of a thermodynamic system, and hence its internal energy. In first case, when we were keeping the cylinder in contact with a body at high temperature, so that time heat was doing the work of increasing energy of the gas. In second case, we were moving piston, so that time we are doing the mechanical work, and because of that work the energy of the system was changing. So heat and work, they are two different modes of changing the state of a thermodynamic system. That means its internal energy. Now see the last paragraph. Heat is energy in transit. Transit means it is always transferring, it is always moving from one place to another place, from high temperature to low temperature. It is not a state variable. Internal energy, as discussed earlier, is the sum of the kinetic and the potential energies of the molecules of the system. It is a state variable. Okay. After zeroth law of thermodynamics, now let's move to the first law of thermodynamics. To understand it better, look at this figure. Here we are having one container, okay. So this is our container here. These walls you can see, the dark one, okay, they are non-conducting walls. The heat cannot the heat cannot pass through these walls, okay, but the base of the container is conducting, is made up of conducting material, okay. Why it is conducting? Because from downward direction we are supplying heat to the container, that means to the gases. On the top of container you can see P is a piston, okay. So here this is our piston. From this part, when we are supplying heat inside the container, the gases are absorbing the heat. Because of absorption of heat energy, their kinetic energy increases, okay. And when their kinetic energy increases, the gases want to move, the gases wants to do more motion, okay. They want to move in more random manner, and in that case they are their energy becomes high, so they move very fast in comparison with when their temperature was low. So now what happened, the number of collision increases, and the gas particles, they do not only collide with each other, but they also collide with piston, wall of the piston. So what happened, when they collide with each other, that time their kinetic energy will increases, okay, their kinetic energy will increase. When they collide with piston, the piston also starts moving in upward direction, okay. And when something is moving, that means work is happening there. So whatever amount of heat energy is transferred to the gas, some amount of that energy is used here in increasing the temperature of the gas, and some amount of energy is used to do work by the gas. Okay, so whatever heat energy is given here is used in two parts. Okay, suppose if we have supplied del Q energy, so it is used in two part. Some part is used to increase the internal energy and some part is used to do the work. Okay, so del Q equals to del U plus del W. This is our first law of thermodynamics. So now let's read the statement. If heat is supplied to a system capable of doing work, the amount of heat absorbed by the system is equal to the sum of the increase in the internal energy and the external work done by the system on its surroundings. Okay, I hope you all have understood this very well. We all know that work done is equals to force into displacement. Now suppose because of work done by gas on the piston has been displaced by a distance dx and F is the amount of force. So we know that force equals to pressure into area. Okay, so del W equals to PA dx. A dx means area into length, that is volume. So del W equals to PdV. Okay, so in first law of thermodynamics, del Q equals to del U plus del W. In place of del W, we will put PdV. So now the equation will take this form: del Q equals to del U plus PdV. So here we can see del Q depends on which factors? First, it depends on the initial and the final state and do not depend on the path. Del Q and del W are path dependent, but del U is independent of the path. And third, internal energy depends only on the state of the system. Okay, so it was first law of thermodynamics. Now tomorrow we will discuss about special case and also some other phenomena related to thermodynamics. So see you in next lecture. Till then, goodbye, take care, do some productive work, and the most important thing, be healthy, be safe.